In the early stages of computer science, there was no clear set of rules on how computers should communicate. In the 1970s, engineers began collaborating in an effort to define one unified framework to regulate computer networks. It was a heated debate, as various competing models were proposed. Eventually, the TCP/IP model, also known as the Internet Protocol Suite, emerged victorious, solidifying itself as the basis of most computer networks, including the Internet. So what is this model all about? The common version of TCP/IP consists of 5 abstraction layers. Let's review them one by one and see what they do. The fundamental units computers work with are bits, zeros and ones. So in order to communicate, they need to transmit streams of bits to one another. This is the responsibility of the physical layer. First, we need a medium for the bits to pass through, for instance, a copper wire. The computers will agree that high or low voltage in the wire signifies a 0 or a 1 and control the voltage to communicate. This kind of agreement is called a protocol, a shared language between devices. Each layer in the model is in fact a set of protocols. Communication over copper wire is a layer 1 protocol, and so is communication over radio or through a fiber optic cable. What places them under the same layer is their task, transmitting bits. The physical component in the computer that handles the transmission is called a network interface controller or a network adapter. So we established communication between 2 computers. Mission accomplished, right? Well, not quite. What if more computers are involved? We could connect each of them to all the rest, but this would get really complicated real fast. A better solution is to use star topology, where all computers are linked to a central device called a hub, which duplicates incoming signals to all other computers. But this has some serious issues as well. If all transmissions are duplicated, how does one device know if an incoming stream of bits was intended for it? And won't all these streams of bits collide with each other and create a mess? And how do we know that what we received is really what was sent? We need something more. The second layer uses the first layer to convey sequences of bits, but defines how they should be organized. What it does is split these sequences into groups called frames. These frames are sent across the network in an orderly fashion to prevent collision. An example for a second layer protocol is Ethernet. In addition to the transmitted data, Ethernet frames contain a header and a trailer with additional properties. Most notable are the physical source and destination MAC addresses. These are values unique to each network adapter in the world, like an ID. This way, every device can know if a received frame was intended for it or not. There are also special MAC addresses like the broadcast address, intended for all devices in a specific network. The value in the Ethernet frame's trailer is used for error checking. If a frame gets corrupted on the physical layer, or if a collision occurs between frames, the trailer value will reflect this and the frame will be dropped. Now that we have all this defined, we can also improve the hub. It is wasteful to duplicate each and every frame. This is why nowadays a switch is used instead, a second layer component that can read MAC addresses and send frames off toward their intended destination. For this, it must store and recognize the MAC address of each network adapter. We can even connect multiple switches and they can collectively carry out this function. A group of devices connected this way, at the second layer, is called a local area network, or LAN. But we still have a problem. The scales we've been looking at are not close to the size of real-world networks. When there are not hundreds, but potentially billions of devices in one network, it is not feasible to have every switch recognize and stay updated about every MAC address. Nor is it possible to allow every device to broadcast a message to the entire network. In short, for large networks, we need another mechanism to enable orderly communication. Layer 3 uses the second layer that enables communication within a LAN. Note that a layer shouldn't care how the layer below it functions. So, Layer 2 could be using Ethernet, Wi-Fi, Bluetooth, or any other protocol. The important thing is that it can move data from one network adapter in a LAN to another. Based on this, the third layer introduces a new network device, the router, which has several network adapters, each placed in a different LAN. This way it can connect local area networks and form a wide area network, or WAN, a network of networks. A LAN may include the devices in your home, whereas a WAN can encompass the entire world. The third layer uses the Internet Protocol, IP. Similar to frames in Layer 2, IP defines packets. These can be intelligently guided across the vast WAN by the routers, letting everyone in the WAN communicate. Packets have headers with many properties, among them source and destination IP addresses. This is where the real strength of the third layer lies. As opposed to the arbitrary MAC addresses of the second layer, these assigned logical values signify where devices are in a larger network, much like an address that would be used for a postal service. The idea is that large networks are split into a hierarchy of subnets, and similar addresses are close to one another. This way, routers don't have to remember every address in the network like switches do. Instead, they recognize subnets and plan out routes across the WAN. Note that a typical router you'd find in your home usually doubles up as a switch, with multiple wired and wireless connections in the same LAN, and a special port to connect outward to the rest of the WAN. But wait, how do the frames of the LAN interact with the packets of the WAN? Here's a quick demonstration. Say Alice wants to send a message to Bob. They are in different LANs, connected by a router. In each LAN there is a switch, and all components are connected with copper wire. To get to Bob, the message must travel across the WAN through the router, so it must be placed inside a packet. The packet will contain the source IP of Alice and the destination IP of Bob. To get to the router, the packet must travel across the LAN through the switch. But communication in a LAN must use frames. Well, since a packet is data after all, it can be transported as the payload of a frame. This process of wrapping one protocol inside another is called encapsulation. The frame's header will contain the source MAC of Alice and the destination MAC of the router. The frame now has to be sent through a physical medium, and so its bits are transmitted as electricity through the copper wire. The frame is reassembled as it reaches the switch. The switch reads the destination MAC address, that of the router, recognizes it, and sends the frame on its way. The frame arrives at the router. The router peels off the frame's header and trailer to reveal the packet inside, and now the process repeats. Using its destination IP, the router determines where the packet should be sent next, and places it inside a new frame fit for the next LAN. At last, the packet reaches Bob, who can now open the frame, then the packet, and read the message inside. All of this can happen millions of times a second. So, did we finally achieve effective communication between many computers? Well, sort of, but two major flaws still remain. First, we are sending data, but we're not guaranteeing that it actually reaches its destination. And second, we want to allow computers to communicate with more than one participant at a time and keep the conversations separate. We must introduce another layer. The fourth layer relies on the third layer to move packets across the network. Until now, we related to computers as performing one conversation at a time. But in practice, they usually conduct many parallel processes, each of which is engaged in a different conversation. In order to separate them, the fourth layer defines port numbers. Not to be confused with physical ports you connect cables to, these are virtual endpoints that can be assigned to processes or services. In other words, ports are like an address for programs inside the computer. Much like frames and packets in the lower layers, the fourth layer defines segments, with headers that include source and destination port numbers. When sent in a WAN, segments are encapsulated by packets. Since programs require different styles of communication, the fourth layer defines two main protocols, TCP and UDP. Each has its advantages and use cases. The thought behind TCP is that it should provide a stable connection, enabling a stream of segments to be sent reliably with their order and completeness guaranteed. TCP segments can take on different roles. Some are sent purely to establish connection or to acknowledge that a segment has been received. Everything is carefully kept track of, and if a segment is lost along the way, it is resent. This is very useful. For example, when you want to transfer files, they can be split up into smaller segments, sent across the network, and carefully reassembled at the other end. UDP, on the other hand, is much simpler. UDP does not guarantee a stable connection and is basically the bare minimum required for ports to be usable. This makes it highly preferable when efficiency is of the essence. For instance, when streaming video or playing an online game. It is also used when there is no need for a two-way connection, for instance, when broadcasting. So we've enabled programs on different computers to share data. But what exactly is this data? This is where things get really varied. In a way, the application layer is the data that the computers share with each other. Anyone developing an application can invent their own fifth layer protocol tailored for their specific usage. This is also where terms like client-server and request-response become relevant, describing which devices should have to communicate in the first place. A common example for a Layer 5 protocol is HTTP. As opposed to the very strict same-sized structures we have seen at the lower layers, HTTP transports readable text of varied lengths. HTTP over TCP is extremely popular in the Internet as it is used to pass HTML web pages to clients. Nowadays, it's been mostly succeeded by HTTPS, a secure version of it. This is why nearly every web page you're on begins with HTTPS. This model, TCP/IP, exists alongside its stricter rival, the OSI model, in which the application layer is split into 3 layers with distinct functions. In fact, the first 2 layers were originally considered one as well. This is why you may see references to 7-layer, 5-layer, and 4-layer models. They are all in use and fairly similar. This is the model in a nutshell. Of course, a short video cannot come close to describing the incredible complexity found in the real world. Every protocol we have seen so far is just an example of what this framework enables. The variety of applications and protocols today is enormous. As opposed to the supposedly independent layers of the model, in reality the line between them is blurry. Networks are a vast, weird place. The fact that any of it actually works is testament to meticulous work by generations of computer scientists and engineers that nowadays we mostly take for granted.